Assalamu alaikum, my dear students. Hope you will be in the best of health, wealth, and happiness. Uh, I welcome you all into my today lecture. Today's our lecture number 15, still Unit 12, Current Electricity. I'm your teacher, Muhammad Ikram, and I welcome you all into the today lecture. Our today topics are Rio State, the sorry for the wrong spelling. This is REH. Okay. The Rio State, the Rio State potential divider, electromotive force in its source, internal resistance of a supply, electric power, and maximum power out. These are our today topics. So let us start with the name of Allah Almighty. Rheostat. Now, what is a rheostat? Rheostat is an electrical instrument which is used to provide what? Used to provide variable resistance. Used to provide variable resistance, right? By the working principle of A's we know are directly proportional to L. So keeping this thing in our mind, we use the rheostat to get the variable resistor. And you know resistor is a device which is used to control the flow of current in a circuit. So variable resistance means that full control on our current or potential difference, that which we can get from the this. If you see the figure of the rheostat, just it consists of two terminals. We call this as the terminal A of the rheostat, this terminal, and then there is another terminal, two, that is, it has two fixed terminal, one terminal A, the other terminal B. This is the fixed terminal, and one we have the terminal C, right? And there is if you just to look to the part of the various part of the rheostat, this is called the kernel part. This one is, you see, this is the kernel part. This is the slider or the sliding contact C, and then you see there is what? There is the brushes. Now the most important point here is that current always choose the path of least resistance. Sometimes people say the shortest path to flow, but it is not right, because it is not the path, it is rather the resistance. So current always choose the path of least resistance. Current always choose the path of least resistance to flow within the circuit. So this is how we will use in our this device, that how it will get the varying resistance. The resistance of the wire between the point A and C, as you see, look, this is point A and C. So the resistance between the point A and C, the resistance of the wire between the point A and C, we can be used if the sliding contact is moved away from the terminal A. Look, this is the sliding contact. If you move it away from the terminal A, if this is the length and if this is the original length, I will label it like this one, the initial. So as you move the sliding contact away from the point A, the length and hence the resistance increases. As you see here, what is going to happen right now, if that is when the C is moved away from what? From the point A, from the point A, then what happens? Then L increases, the length increases, what? L increases. So if L increases, you know, R is directly proportional to length, so resistance increases. What happens? Resistance increases. You see increase in the resistance, right? Uh, and when the sliding contact is moved towards towards the point A, then what happens? That L decreases and the current increases, the resistance decreases. How? Look here, what is going to happen? You see that these are the wires that moves around this cylinder, right? Since Rio State is the wire wound variable resistor. So you see, look, these the number of turns is the current flowing in this, as you see like this. Okay, so when they see the path of least resistance, because there are more thousands and thousands of turns, and here it is just direct a simple look, direct a simple connection like this, and this is how the current will then flow through this. So you see, as you move the slider, then the length increases. These brushes which you see here, look, they make connection with the wire as well as what? As well as with the slider, right? So this is how the current will be controlled in the circuit by using this variable resistor. So this rheostat plays a very important role in controlling the current in a circuit. This can be used as a potential divider. And now I will explain to you how we can use the rheostat as a potential divider. Potential, potential divider, potential divider. Potential divider is a device which is used to, a device or electrical instrument used to provide potential difference, potential difference from 0 to the full potential difference of the EMF source, to the full potential difference, the full potential difference of the EMF, of the EMF source in the circuit. Now this, what does this means? Providing varying potential difference. Providing what? Provides varying potential difference from 0 to full or maximum. From 0 to full or maximum potential difference of the battery. Now look, as you see here, look at this diagram. Just take it back down. And also this one here, and let me have this is right. Sorry. Now let us see how this happens. Let us consider a circuit, right, which is connect. Let us consider the circuit. In the circuit, this portion or this part, this acts like what? This portion or the part acts like the rheostat. Okay, the rheostat part of the circuit. There is EMF source. There is what? There is the EMF source. This one is our EMF source, right? The external potential difference that is provided in the circuit, and this causes the current to flow. Since there is only one path for the flow of current, so the current starts from the positive terminal of the battery and then it leaves in this way. Now you see that it is the sliding contact. Here you see look, that is what? That is the sliding contact point C. So as you move C, then what happens? RBC changes, and when RBC changes, the potential difference across these endpoints also changes. How? The total current in the circuit, here we have I that is flowing in the circuit. Now look, if you just see that what is the net or the total current that flows in the circuit. So from the diagram, from the circuit diagram, from the circuit diagram, we want to calculate this VBC. Okay, from the circuit diagram, which is our input, we know that the total current that is flowing in the circuit I, that is equal to V, that is just what I call this V input as V. Okay, that is V by R. R is the resistance of the circuit. Okay, now let us see that is you know that I told you in the previous topic that current always choose the path of least resistance. Now you see, as you move the sliding contact, then the resistance RBC get changed, and the potential which you can get around this point, we call this potential as the VBC potential. Now what will be this VBC potential? This VBC potential, VBC, it will be equal to the current times the resistance at this point. Now, what is that resistance? That resistance is the RBC resistance. So this is what the potential difference you can get. Now, as you see, look, what is going to happen? Now, let us see, this VBC will be equal, since as we know that it is V always equal to Vn, that is Vn. I'll be writing it as Vn. This is best. Okay, so Vn n by R into RBC, as you see. Now from this equation, the VBC, the potential difference across the point V and C, will be equal to RBC into R into Vn. Now, what is this R? You know, R is the origin, that is the equal to the original length of the resistance as R equals L. So you see that that is the initial resistance of the wire A when at its total length L. Now you know that when the resistance change, when the length changes, the resistance get changed. So RBC is actually the portion of the resistor between C and B. Yeah, it is the resistance between the point C and B, which is this one. Now you see that, look, R is since fixed, the only way which we can get change the VBC is which one? The VBC. Now this shows that it is directly proportional to what? To the RBC. So if the RBC get changed, the VBC get changed. And what does this mean? That the RBC can be the ratio of this RBC to BC. This can be RBC to R. This can be varied. Yeah, this can be changed from what? From 0 to 1. From 0 to 1. So how this can be done? When the sliding contact, when the sliding contact C is moved towards B, then the length and hence the RBC decreases, and that is when RBC is moves towards the point B. Look, if you move the C towards the point B, then what happens? The RBC decreases, and when RBC decreases, VBC decreases, and once that is when the point C, when the point C arrives at what? At the point B, then what happens? RBC becomes what? 0. And the resistance will be, that is the potential difference will be what? It will be 0 at this point. right? And now when you move the VBC from this point, from the point B towards the point A, RBC increases, the potential difference increases. And when you arrive at the point A, then what happens? That RBC becomes equal to R, and the battery, the output will be provided to you will be equal to the input of the total input of the circuit, right? So this is how the Rio states works. Sorry, the potential divider works. So the potential divider can provide you varying potential difference from 0 to the maximum, right? But remember, just note it down. We cannot cross the V out, cannot cross the V and Y because this is your input, right? So output cannot be greater than your input. So only you can get it from what? Between 0 and that maximum value, right? So that is all about the potential divider. What is the next topic? The next topic is the electromotive force and the source of EMF. So let us study about the electromotive force. What is electromotive force? Electromotive force, or sometimes we call the EMF. This is a mistaken term. In fact, there is no, it is not actually a force, rather it is what? It is a kind of electric potential. It is a mistaken term. So why it is called the electromotive force? I'm coming towards that point and then I'll be telling to you. Let us to explain the phenomena of the electromotive force. For example, in this world or in this universe, nothing happens without anything, right? That is that we cannot have energy without sources. So electromotive force is in fact what? It is the source, or we can say that it is the strength of what? It is the strength of the battery to drive electrons around the circuit. That is the strength of the battery to drive the electrons around what? Around the circuit. So what does this mean? In fact, this is our input. So if this is our input, then it will be what? It will be the work done on the charge. The work done on what? On the charge to move it around the circuit. Around what? Around the circuit. So this is what the external energy. That energy is provided by the chemical energy stored in the battery. So what does the battery do actually? The battery pumps electrons, right? Yeah, it removes electron from the positive terminal, places it on the negative terminal, potential difference is created. And if I just take the actual current direction, then the electrons are being moved around what? Around the circuit. So this is what actually the work done on what? The work done on the charge to move them around the circuit. And this is known as the electromotive force. And this electromotive force, and it is the work done on the charge. Contrary to this, we have the potential difference. The potential difference. What is the potential difference? Potential difference is in fact the amount of energy released as the charge move around the circuit. So potential difference is in fact the work. It is what? It is work done by the charge. Work done by the charge. So that is our output in fact, right? And it is the same formula, work done by the charge as they move around the circuit. So potential difference is related to the situation where electrical energy is converted to non-electrical energies, right? While electromotive force is related to where the non-electrical energy is being converted to the electrical energies. Both are measured in the same unit. Potential difference as well as these two. Both are measured in volts. The SI unit is what? The SI unit is volt. So both are measured in the same unit. So electromotive force, in fact, what? It is the strength of the battery to drive electrons around the circuit. Now, it is called the electromotive force because why? The battery sets electric field inside it, and the force due to this electric field causes the electrons to move in the direction opposite to the direction of the electric field. For this reason, they are called what? The electromotive force, right? So this is the phenomena of the electromotive force. Electromotive force, SI unit, as I told you, volt, right? Measured in volt. And the electromotive force exists even when the circuit is open, even when the circuit is what? Even when the circuit is open. It is just like when you switch off your smartphone. When you switch off your smartphone, still the battery have energy in it. But contrary to this, the potential difference, this only exists when the circuit is closed. That is the main difference. When the circuit is closed, right? For example, when your mobile is switched off, then you cannot see, you cannot connect a call, you cannot receive a call, and there is no activity. Why? Because there is no potential difference, but indeed there is the electromotive force, right? So that is all about what? That is all about the electromotive force. There are the sources of the electromotive force also, and the sources of the electromotive force includes the batteries and cells. Cell is one unit of electricity and convert chemical energy into electrical energy. Batteries consist of two or more cells together, either combined in a series to provide you greater potential or in parallel to provide you the greater current. And there are electric generators also. So sources include cells convert chemical energy to electrical energies. Batteries consist of two or more cells combined together, and we have the electric generators also. And the electric generators convert mechanical energy into electrical energy. And we have the thermocouples also, and thermocouples convert the heat energy into what? Heat into the electrical energy. And we will explain all these at their appropriate places. And then we have the solar cells, or the radiant solar cells, which convert light energy into electrical energy. So these are all about what? These are all about the sources of the EMF. Now our next topic is about the, and that will be the internal resistance of the supply. The supply is, of course, electromotive force. The internal, our next topic, let me check, but I think I remember. The internal resistance, the internal resistance of supply. Now, what do we mean the internal resistance of the supply? Let us talk about the, let us consider the electric circuit. As you see, our electric circuit consists of the EMF source. This is our EMF source, as you see here. The EMF source, this is our, you see, this is our EMF source, as I label it as this one. The you know that there is chemical, and almost all conducting substances have some resistance. So definitely our battery has some internal resistance, and the internal resistance of the battery is marked by small r. This is what? This is the internal resistance, internal resistance of the source or battery. Okay, this is the load resistance. Okay, here we have what? Here we have this one is the load resistance r. This is what? This r, it is the load resistance. Load are the external resistance. External resistance. Okay. So you see, look, this is your what? This is in this circuit, this is your what? This is your input, as you see. Your entire input is here. Let me label it as your input. This is our what? This is our input. Now, physics is all the game of energy. So we would like to look that where the energy can be consumed. So of course, one is this point. The sum of the energy is utilized in overcoming about the battery own internal resistance. So therefore, one, we have the potential drop here, the potential difference drop, yeah, the potential drop here. And what could be that potential? I am coming to that point. One, we have the potential difference across here, right? And that IR drop, your teacher is going to label this as V. We call this potential difference across the terminal of that load or internal resistance. We call it the terminal potential difference. It could be marked VT also, or simply I will write terminal potential difference. Terminal potential difference. This is what we are interested in, that what potential difference we are getting at the point D and C. Okay, so this is our output. This is our what? This is our output. Now this is neither our input nor our output, but that is what the battery own internal resistance, and this is what it is going to be wasted. So we are not getting the full potential difference in a E, that is E never be the same as V. Input never be the same as output never be the same as the input. Why? Because some of the energy which we provide can be utilized in overcoming the battery on internal resistance. Now, as you see, look, what is the total current that is flowing in the circuit? The net current, according to the Ohm law, according to the Ohm's law, V equals what? V equals IR. Now, what is this R? This R is in fact the total potential difference, the total resistance of the circuit, right? And what is this V? This V is in fact whatever the external potential difference you are providing. So this is how I can adjust my equation. Now, what is this total resistance of the circuit? The total resistance of the circuit is equal to the load resistance plus the battery own internal resistance, which some of the energy is being dissipated in the form of heat energy, right, to overcome the battery own internal resistance. And if you are very much meticulous and sensitive, then you can even include the resistance of the wiring also, but for this it is enough. Now let us see that how I can write this equation, that it could be like I, and it could be R plus R, right? Or we can say that we have the IR and we have what? The IR. Now, what is this portion of the equation? This is in fact what? This is in fact the terminal potential difference. Sorry, this is the battery, the potential drop across the battery, potential drop, potential drop across the battery on resistance, the source on resistance. This much energy, this is not we are going to get this. So what here is the output, the terminal potential difference? The terminal potential difference is in fact this one. This is how we can calculate the terminal potential difference for any circuit. This is what the potential difference which we will get across the load. So the factor IR, this is called terminal potential. And the terminal potential equals like this. Okay. Or from this equation, we can also say that the current in the circuit, the total current in the circuit is not the EMF source by R, rather it is equal to what? R plus R. This is the total circuit of the this thing. Now, what happens? There are many cases. Okay, if the circuit is open, for example, cases, one such case I will tell. For open circuit, what happens? For open circuit, I will become equal to what? 0. And what you will be having? You will be having your this terminal potential difference V. It will become what? It will become, this V will become that the source of the EMF source, the potential of the EMF source. And there is no other way, right? For which V becomes the electromotive force, the external the terminal potential difference becomes the EMF, equal to the EMF of the circuit. Okay, this is only when the circuit is open, and the rest, that is, this is case A. Case B, for closed circuit. This could be this could work best for your MCQs. For closed circuit, for any closed circuit, as there is a current flowing in the circuit, so we must be less than this always. And this is what the law of conservation of energy is, that even the law of conservation of energy is validated in the electrodynamics also. So we cannot get rid from the law of conservation of energy. What could be our next topic? Maybe electrical power. Let me check. Okay, and the electric power. That what is the electric power? The next topic is electric power. This is what you have studied in class 10, and I will only give the basic concepts and idea here and nothing more. Electric power is any power we define as the rate of what? It is as the rate of doing work done. But the electric power is in fact equal to what? The electric power is the rate of what? Doing work done. Now, what does the electric power tells you? That how fast electrical energy changes into non-electrical energies, this is what we will learn here. So the electrical power is equal to the rate of doing work done, and we know that W is equal to, from the Joule law, as he stated, the amount of electrical energy dissipated in the circuit is equal to the square of the it is equal to the product of the square of the current flowing in the circuit, the resistance of the circuit, load resistance, and the time for which the current flows. So definitely then it will be equal to I square R into T. The Joule law, you have already learned about the Joule law in the previous class, okay? So this is why I don't want to comment much on it. And this will be equal to T. And what will be your power? Your power will be equal I square R. Power is measured in watt. The unit of the power is watt, kilowatt, and megawatt. For commercial purposes, we use megawatt because watt is a very small unit. Okay. Now about the kilowatt, you might have heard kilowatt. Remember kilowatt hour. Kilowatt hour, it is not the unit of power, it is the unit of energy. Unit of what? It is the unit of energy. You must remember this. Why? Because kilowatt is power and R is time. So if you remember the equation, like what is this WP into T. So if you take the power in kilowatt and if you take the time in hours, so kilowatt hour will be equal to what? It will be energy, not power, and it is the commercial unit or the industrial unit of energy. And 1 kilowatt hour, you have learned this thing in class 10, that it is equal to 3.6 into 10 into 10 to the power 6 joule, or 3.6 megajoule, or we can say 1 unit of electricity. 1 unit of electricity. No need to discuss this in detail here, but just let me come to this point again. So P is equal to what? P is equal to I square R. So this is what? This is the power, the amount of heat energy, the power, the rate dissipated across the load resistance R. Now for the battery, if I just write this way, then sorry, the small r, this is what actually I want to tell you. So this is for what? This is for the load resistance. For what? Sorry, for the power consumed in the battery on, yeah, internal resistance, battery internal resistance. So there is a greater difference between the two. You now, class 10 is over. In the second year, you must be very careful because every intricate detail should be included. So this is the power across the resistor, and this is the power across the battery on internal resistor. Similarly, we can also write, if I just put here the V by R, then V square by R. So this is what you can calculate the power by ignoring the battery internal resistance. This is across what? This is the power across the, that is the terminal resistance, right? And similarly, for the power of the battery, we can have this thing also, clear? Similarly, we can write the power I into V. Okay, this is usually used to calculate the internal power of the battery. I don't want to discuss this because you have learned already in this thing in your class 10, but these are the simple formulas which you can use for the further. So our next topic is the maximum power out. Okay, maximum power out, that when a given electrical circuit can deliver the maximum power out. So let us do this for the maximum power out. Is right now, I told you a few moments before that our terminal potential difference, the will be V will be here, right? And this will be our electromotive force, and we want that how much maximum power we can get here. So as we know that, as we know that the power out will be equal to what? It will be equal to IV, as I told you that it is the power delivered, what? Power delivered across the load resistance, across the load. resistance. So we have this thing R. We can write this power out as I square into R. But if you remember, I told you seconds earlier that this I is equal to what? It is equal to this into R plus R, right? So let me replace the I here in this equation, and we have this R plus R into whole square into R. So the power out will be, this will be equal E square into R into R plus R. Now for the maximum power out, right, we should have the denominator minimum, that is, it should have minimum one. So the power will be maximum if this is what? If this is minimum. We cannot arrange it in this way. So let us make certain changes in our equation, which will not make, or which will not alter our equation, but it will help calculating the maximum power. What if I write R so that to make the denominator minimum, okay? To have a maximum power whole square into what? Into plus 4R into R. Okay, so if you expand this, definitely you will get the R plus R again. This is what I did. Right now for the maximum power out, that is the power will be maximum. Power out has to be power max if the denominator is what? If the denominator is small, and it is only possible when the factor in the denominator is 0. What does this means? When R becomes equal what? When R becomes equal to R. What does this means? That the that is the, when the, that is what? That is of course the load resistance. So this is maximum when the load resistance becomes equal what? The internal resistance of the battery, and the, that is, and then the circuit will deliver the maximum power out, right? So what does this means? That this is in fact the result, you must focus on this result which I'm going to write, that the least power, sorry, that the least resistance has the greatest wattage. जितना रेजिस्टेंस कम होगा उतना ज्यादा पावर उसके एकरास क्या होगा? उसके एकरास डिलीवर होगा. सो आवर पावर आउट, द मैक्सिमम पावर आउट, it will be equal what? It will be equal to EMF source, this R, and we have that thing 0, and we have 4R square. So the maximum power, sorry, power max. So the power max will equal to this thing, so which is only possible when the load resistance becomes equal the battery internal resistance. So this is our today lecture. Uh, Thank you very much for being here, and inshallah see you in the next lecture. Thank you very much.